All right, gang. Now what we're going to do now is try to get an estimate of the intrinsic variability remaining, okay, given that we've taken out that car-to-car variability. Well, you know, we've actually thought now in terms of another mathematical model, a new mathematical model, and with this new mathematical model we can do an associated analysis of variance, subtracting out or deleting the variability due to car-to-car differences. So let's see this other analysis of variance table. Now the model has to change. And the only interesting, and the only but most interesting difference in this model is there the observation equal to mean performance plus contributions due to the different treatments plus contributions due to the different blocks. Right? And that is the car-to-car variability. The heavy cars would add, the very light cars would subtract, and then other errors such as drivers and weather and shape of road and so forth, which we continue to assume to be normally and independently distributed. This changes our analysis of variance table in only one essential place. The residual sum of squares is now going to be partitioned into two pieces. It's going to be partitioned into a piece due to cars and into a piece due to residuals. And we're going to call this partitioning the block sum of squares. I need a sum of squares attributed to the differences between blocks, or if you will, the differences between the two cars. Let me show you the equation for getting the block sums of squares. This is really a very familiar equation. You may have recalled what the equation was for the treatment sum of squares. And here's the similar equation for the block sum of squares. You take the block totals, square them, divide by the number of observations in the total. Do that for each block, summing up that group and subtracting out the correction factor. If, as we've managed in this case, to have the number of observations in each classification the same, in this case each one of these n's is equal to 2, then the equation is much more simply just 1 over n times the sum of the squares, the treatment of the block totals. Now we could have got the block sum of squares another way. We could have estimated those little block effects and taken their sums of squares. But this is the rapid means for doing it. I've employed this particular equation in getting the block sum of squares, so let's return to our table and see what's happened in this instance. The block sum of squares is really a whopper. It turned out to be 110.4905, and what did that leave me for my residual sum of squares? Not very much at all. Our residual sum of squares, gotten by subtraction now, is equal to 0.6745. And now let's worry this degrees of freedom column. How many degrees of freedom does the block sum of squares have? Not 10, 9, because if you see where once again these block effects are constrained, and if I knew 9 of those block effects, I could always calculate the 10th. Since they are constrained in the algebra, they're forced to equal the sum to equal 0. So we have 9 degrees of freedom for the block sum of squares. And then how many degrees of freedom would that leave over for estimating the variance in the residual sum of squares? Well, similarly, 10 from 19 would leave 9. And my estimate of the intrinsic variability is now the 9 degrees of freedom into the residual sum of squares are now s squared is equal to 0.075. And the expected value of that quantity, of course, is sigma squared, an estimate of the intrinsic variance. And what happened in this case? We have partitioned the other residual sum of squares into two components. In other words, the residual sum of squares with the earlier model, without the block effects taken out, was 110 plus a bit. And now you see that 111 plus a bit. And now you see that 110.4905 of that has been consumed by the block-to-block, that is to say, the car-to-car differences. And now there's our residual sum of squares. And similarly, our 18 degrees of freedom, which we had earlier, have been partitioned into two groups of 9. All right, gang. Now we have another estimate of the intrinsic variability of the data. Let's go back and make our interval estimate all over again. So we'll come back here. Let's see now. S squared is going to be different. And if S squared is different, and it's going to be based on another number of degrees of freedom, then T will have to be different as well. So I have two substitutions to make here. My S squared turns out to be 0.075. Okay. And what do you think the T is? It will be a T with how many degrees of freedom? It's a T with 9 degrees of freedom. And T with 9 degrees of freedom is, look her up, T with 9 is 2.23. So just plug in a 2.23 here for T. Okay. Now, What happens when I turn that crank? The difference between the averages is still 0.41, but now this statement is considerably changed. And instead of reading that for our interval statement for the difference between the means, we now see 0.1 plus or minus 0.28. And if I substitute in there, I find out that my lower limit turns out to be 0.13 for this parameter, and the upper limit is 0.69. And here's an interval statement for the difference between the two means. And how do I interpret this statement? I say, you know, all values of eta 1 minus eta 2 which lie inside this interval are not contradicted by the data. This is a 95% interval statement for the difference between the means. Now, once again, this is merely a symbolic demonstration of what's going on. It's in our very real interest to get a picture of what's going on. And so let's return to the board and see what that interval statement looks like when we can use it here. So here is the scale. We still have the same statistic. It's still equal to 0.41, but now my limits run from 0.13 right, up to 0.69. And that's what I now know about the true difference between the means. And pray, what would happen if I had, using the analysis of variance table, set up the hypothesis that there was no difference between the means? Right, that would have been the same thing as saying eta 1 minus eta 2 is 0. And where, pray, is 0 in this case? 0 is outside the interval. And so had we performed that test of hypothesis using the analysis of variance test, we would have observed a rare event F, and we would have been compelled by that analysis to dismiss the null hypothesis. You may remember the other limits were 2.74 and a minus 1.92. And look at the gain in information that we have picked up as a consequence of designing this experiment, this more clever way of employing a randomized block design by blocking out a source of variability and accounting for it in our analysis. We've been able to make a much more informative statement about the difference between the gasoline with additive and the gasoline without additive and its performance on those various cars. Okay. Now, gang, there happens to be another way of doing this kind of a calculation. It's called the paired T. This is really a randomized block experiment. We've had the experiment chopped into blocks, the blocks being cars, and we have randomly assigned the treatments within the blocks. Now, so long as there are only 2 treatments randomly assigned within the blocks, we can do all the calculations another way. We can make an interval statement for the true difference between the means employing T. And this use of T is called the paired T. Now, to do this, we attract our attention to the differences. It's the differences which carry the information relative to eta 1 minus eta 2. And we see displayed here the 10 differences which we ran into as a consequence of running these experiments. You'll notice some of the differences are even negative. That means, you know, the additive apparently has a deleterious effect on the mileage of these cars. So that variability we see here is intrinsic. It has the car-to-car variability left out, and at the same time there is other source of variability obviously there. What I want you to do now, I want you to imagine those differences as observations. I agree they're contrived observations. They are, you know, the differences between 2 elemental observations, but just think for the time being that we have 10 observations, except they're differences, all right? And now let's go ahead and do our best to analyze those data. So I'm going to have the 10 observations. I'm going to determine what their average is, and then I'm going to make an interval statement for the true difference. That is to say, I'm going to make an interval statement for delta, the real difference. Now, I've done all that. That doesn't take much time to do. What do you think the average of those differences would be? What do you think the average of those differences would be? And it turns out the average of those differences was just what it was the last time, 0.41. And it turns out to have n equals 10 of these differences, these new observations, 10. Okay, now I've estimated the variance. S squared d turns out to be 0.15 with 9 degrees of freedom. I put that d down there to remind me I'm working with these contrived observations. All right, what does this statistic estimate? It estimates delta. So let's make an interval statement for delta, and that's easy enough to do. the interval statement for that parameter. The limits would be given by the statistic plus or minus the critical value of t times the variance of that statistic. So there's the variance of the things that made up that statistic times 1 over n. And now let's just quickly substitute ahead here. D bar was 0.41. And let me see, I had 10 observations in the first treatment. And the estimate of the variance is 0.15. And what do you think I have to use for t? How many degrees of freedom does this t have? This t has 9 degrees of freedom. So I end up using the same same value of t I had previously, 2.23. So if we plugged a 2.23 in there, and were to perform that particular calculation, what would we get? And gang, if you were to go through that calculation, you would end up with the same limits for delta that you ended up with for eta 1 minus eta 2. We would say in this case, you see, that all values of delta which fell within these limits were not contradicted by the data. One interesting thing comes to mind here. Why is this s squared equal to 0.15 and this s squared equal to 0.075? This is the s squared based on the differences. And the difference, the variance of a difference, is 2 sigma squared. Well, of course, this estimate will be twice this estimate. This is the estimate of the variance of the observations. Okay, now, I think we are entitled to a quick review. You've learned an important idea in all of this. You've learned that we can take out assignable sources of variability. The thing we really wanted to study was the difference between the treatments, but our study was in a sense contaminated by the fact that we had these car-to-car differences to contend with. But we can balance out those differences. We can block out those differences. And so we have a class of experimental designs which we call the randomized block designs. The blocks in this case were the cars, and you notice that we randomly assign the treatments within the blocks. And with this class of designs, we're able to oftentimes decrease the variability to the extent that we can learn a great deal more about what the true differences are between different means. Okay, gang. Well, I guess it's time to return to our toys. And I suspect I might just well do some more randomization. You remember the essential thing is some aspect of randomization has to attach itself to every experiment. And so let's randomize anew.